So this is the second part of groups and group actions. So just to remind you where we ended up in the last lecture, we proved Lagrange's theorem, deduced some consequences of it, and in particular, we could find how many groups are of these sizes up to isomorphism. Yeah, certainly up to size 7, we could prove that the possible groups are just as listed as in this table. And I indicated that groups of size 8, there are 5 of them. And the next thing one can do is, we're going to do later in this course, we're going to find how many groups are there of size 9. It turned out just there are 2 of them. But to do that, we need more tools. Yeah? So just Lagrange's theorem is not enough to study this. And this is what the second part of the course will be about, to build more tools to study groups. When we talk about group actions, I just want to give you an illustration of application of a group action. I haven't talked about group actions at all so far. This is not a definition of a group action, just an example. So there's this combinatorial object called a graph. In particular, this particular graph is called the Peterson graph. So it has vertices, which I've labeled with integers from 1 to 10, and a set of edges, which are basically, I've indicated them by drawing segments between pairs of vertices. So the edges of a graph are just 2-element subsets of the vertices. Yeah? There's no notion of a distance or anything like that. This is just a combinatorial object. Yeah? So this graph has 15 vertices, 15 edges. So for example, 1, 2, 2, 3, 4, 10, etc. And one question is, how many symmetries has this graph? So symmetry of the graph is just a permutation of the vertices which sends edges to edges. Right? It's a very easy to define. From the definition, you can see that the set of symmetries forms a group, because you can compose symmetries, you can invert symmetries. So one question is, what is the symmetry of this graph? What is the group of symmetries of this graph? So we're going to find an answer to this question later in the course. Okay? This is just to give you an indication which direction we'll be going towards the end. But now let's focus on building more tools to study groups. Well, one motivation comes from vector spaces, for example. So when you studied vector spaces, one of the first things you proved is you classify the vector spaces just on the basis of finding a set of a basis of a vector space. So if you have a few scalars, say the reals, a finite dimensional vector space is determined completely by its the size of its basis. Yeah, n-dimensional vector space. Is completely described by the integer n and the scalars r. So on their own, vector spaces are not so interesting. Yeah? There are not so many of them. But what makes them interesting is the linear transformations, the map between them. Yeah? Once you start study maps between vector spaces, then you talk about matrices, eigenvalues, determinants. The theory becomes much more interesting. Similarly, in groups, one way to make the theory more engaging and deeper is to study maps between groups. Okay? We've already studied isomorphisms. Yeah? I have defined what is an isomorphism between two groups. But that's too restrictive. Yeah? This is just saying the two groups are the same. They have the same Cayley table. The more general notion should be the analog of a linear transformation of a vector space without requiring to be bijective. Yeah? And this is the notion of a homomorphism. So definition. So let G and H be two groups. a map F from G to H is a homomorphism if it has the following property: F on the product of two elements is F of A product with F of B for all A and B in G. Okay? So this product here, let me just be clear, this is the product of two elements in G, and here this is the product of the images in H, right? All right. So homomorphism, put simply, is a map between groups which is compatible with the multiplication. Yeah. Okay. Think about vector spaces and linear maps. They're compatible with addition, for example. Yeah. F of A plus B is F of A plus F of B, right? So this is the analog for groups. This is the definition of a homomorphism. Let's do some examples. All right. Maybe I should start with vector spaces. V and W, two vector spaces over the same field, and then any linear transformation T from V to W is a homomorphism of the groups of the additive groups. Yeah. Of course, the linear transformation is more than that. Yeah. It also has to be compatible with scalar multiplication, but here we only concerned about the group structure under addition. Okay. Example 1. Example 2 is the determinant. Another very useful map. So given a map from GL and F to the, so given any field, we can consider the determinant map, basically the matrix A goes to the determinant of A. Okay, so again, it's very easy to check that this is the homomorphism because the determinant of a product of matrices is the product of its determinants. Yeah. 3. Suppose that G is the complex numbers under multiplication, and H is the positive real numbers, and F of a complex number Z is the absolute value of a complex number. Okay? Okay. C star just means the non-zero elements of C under multiplication. Okay, that's another example of a homomorphism is when we take absolute value of complex numbers. Again, being a homomorphism is just saying that the absolute value of a product of two complex numbers is the product of the absolute values. Okay. All right. So I hope this kind of is convincing that homomorphisms occur naturally, and they're worth studying. So what properties of a homomorphism we have? Proposition. What can we say from the defining property of a homomorphism? Let F from G to H be a homomorphism, be a group homomorphism. Then we have the following. First, F sends the identity of G to the identity of H. Okay? f sends the inverse of an element to the inverse of its image, all G and G, and C, f sends nth power, f sends G to the n to f of G to the n, again for all G and G. Okay, so let's prove this. Okay, here's the definition. Right? Well, what can we do? I mean, at this stage, we just have to exploit this as much as we can. Suppose we take A and B to be the identity in G. Take A and equal to B to be the identity of G, and apply the rule. So we have f of the identity times the identity must be equal to f of the identity times f of the identity. But this is just f of the identity, right? And now we can cancel one f of the identity and deduce that f of EG is EH as required. Okay. Now B. Well, what can we do with B? Well, we're going to now apply what we know from A. I know that the identity in H is f of the identity of G by A. The identity of G is G times G inverse for any G in G, right? But this, by the rule that we have for homomorphism, this is f of G times f of G inverse. Okay? So these elements together multiply to the identity of H, therefore they're inverses of each other. So therefore f of G inverse is the inverse of f of G in H. Right? Okay? And I'll leave the proof of C for you for just use induction. Very it's an obvious induction that can also prove C. Okay. So now we can further expand on the definition of a homomorphism by specializing what this homomorphism will be. So let's do another definition. Let f from G to H be a homomorphism, be a group homomorphism. This is actually more about notation rather than definitions. F is said to be an endomorphism of G if basically G is equal to H. So if in the case when G is equal to H, we call it F an endomorphism. Okay. When F is bijective, we say that F is an isomorphism. Between G and H. We've already seen this definition of an isomorphism. And finally, when G is equal to H, so when we combine the conditions, the two conditions above, so when we require both that G is equal to H and F bijective, we say that F is an automorphism. Okay. So let me give an example of an automorphism. Well, one easy example, of course, can be immediately given from vector spaces. We take a bijective linear map between the same vector space. Yeah. But let's do something more interesting. Definition. Let G be a group and an element A be in G. Define the map. Maybe I should call it a proposition actually. The map theta A from G to G given by the rule theta A of x is equal to ax A inverse for any x in G is an automorphism of G. Okay. So remember, this was 2 elements were called to be conjugate if they're related by this rule. So this is called, this map is called the conjugation map, right? And the proposition says a conjugation map is an automorphism of the group. Okay, so we've already seen this map, but now I'm claiming that it satisfies the condition of being an automorphism. Okay, proof. Well, let x and y be in G. So what we need to check? We need to check, first of all, that theta A is a homomorphism. So we need to check that theta A of xy is it equal to theta A of x, theta A of y. Well, let's check it. On this side, by definition, this is A x y A inverse, right? On this side, this is A x A inverse, and this is A y A inverse. So when I multiply it, A cancels with A inverse, and we end up with these being the same, right? Hence, indeed, hence theta A is a homomorphism. Now we have to check that theta A is bijective. Well, suppose that theta A of x is equal to theta A of y. And I claim that x must be equal to y. Okay? Why? Because this means that A x A inverse is equal to A y A inverse. And of course, we can cancel A and A inverse on both sides and deduce that x is equal to y. Therefore, theta A is injective. And for surjectivity, given any x in G, we find y in G with theta A of y is equal to x. Which y we have to take? Well, it's not hard to see. Choose I'll just cut it directly to the answer. Just choose y to be this element, and then verify that theta a of y is a inverse x a inverse. These cancel, so this is x as required. Okay. Hence, theta a is bijective, and hence an automorphism. Of G. Okay, so we have our examples of an automorphisms. Well, once we talk about automorphisms, we can actually compose them, and they form a group of their own. So definition: the automorphism given a group G its automorphism group denoted aut G is the set of all automorphisms, right? So this is the set O f from G to G, such that f is an automorphism. With composition, with product given by composition of maps. Okay. So if you take the set of all automorphisms of a group, and then we allow ourselves to compose them as maps, so it's very easy to see that composition of, so I'll leave the proof of this as an exercise, yeah? So exercise to check that out of G is a group. Okay, this is in the problem sheets. Very easy to access. All right. Okay. So we have written down a lot of definitions. Now, what can we say about it? What can we say about homomorphisms? All right. Well, the first thing that one can deduce is for example, here is a proposition. Let F be a homomorphism of groups and take an element G in G, then if the order of G is finite, then the order of f of G is finite, and the order of f of G divides the order of G. Okay? right? So actually I don't need the first then. I think it should be an if. Okay, proof. Well, we're given that the order of G is finite, so let n be the order of G. Remember, this is the minimal positive integer such that G to the n is the identity, right? But now we apply f to this equation. So I have then that the identity of H is equal to the f of the identity of G. So this is f of G to the n, and that is f of G to the n by the property of homomorphisms that I left as a exercise with induction. And therefore f of G has finite order. And by the properties of an order of an element, the order of f of G divides n. As required. Right. Proof. As a consequence of that, in the case of automorphisms, we actually can deduce that an element and its image have the same order. Corollary. If f from G to G is an automorphism, actually, if f from G to H is an isomorphism, more generally, then the order of f of G is equal to the order of G for any G in G. Okay? Right, so isomorphisms preserve the order of elements, yeah? And the corollary follows from the proposition simply because we just apply the proposition to f and f inverse, and we deduce that the order of G on one hand divides the order of f of G, and also the order of f of G divides the order of G, therefore they're equal, if finite. And if they're infinite, then they're both infinite. Okay? In particular, it follows that conjugate elements always have the same order. Yeah? So corollary, if x and y are conjugate, elements of G, then the order of x is equal to the order of y. Yeah? Because being conjugate means that there's a conjugation map that sends one into the other, but the conjugation map is an automorphism, so an isomorphism, and therefore it preserves the order. Right? So I'm just combining the above corollary with the conjugation map. Okay? All right. So one of the basic results in linear algebra about linear transformations says that the image of a linear transformation is a subspace and the kernel of linear transformation is a subspace. Yeah? So it's not surprising that similar results hold for groups as well. So let's prove this proposition. Let F be a homomorphism, be a group homomorphism. Then the image of F is a subgroup of G, and the set kernel of F. What would be the kernel of F? It would be the pre-image of the identity of H. So these are all the elements G in G, such that F of G is the identity of H, is a subgroup of H, right? Subgroup of H, thank you. Yes. And this is a subgroup of G. Thanks. Yes. Okay. Right. Proof. I will prove that the kernel of F is a subgroup of G and leave the image of F subgroup of H for you as an exercise. And it's entirely similar to the argument for vector spaces. So we will prove that the kernel of F is a subgroup of G. Okay, so we're going to use the subgroup test. Okay, first of all, the kernel of F is non-empty because certainly contains the identity of G. Yeah, so certainly the identity of G is in the kernel of F. So kernel of F is a non-empty subset. And now suppose that X and Y are in the kernel of F. I need to check that X inverse Y is in the kernel of F. And so what we do, we just verify it by applying F on X inverse Y. Well, since F is a homomorphism, this is F of X inverse F of Y. And by the property of a homomorphism, the F of an inverse, image of an inverse is the inverse of the image. So this is F of X inverse F of Y. But X and Y are in the kernel of F, so F of X and F of Y is the identity. So this is the identity of H inverse times the identity of H. So this is the identity of H. And so by definition, X inverse Y is in the kernel of F as required. Hence, kernel of F is a subgroup of G. And as I said, for the image of F, it's entirely the same. Yep. So far, so good. It looks like very similar to vector spaces indeed. But now there'll be a difference. Because in vector spaces, the addition in vectors is commutative. So it's actually a very special group, an abelian group, right? And we know many groups are non-abelian, and we could expect that there should be some difference from vector spaces. And indeed, the kernel of F is not just any subgroup of G. It has an extra property, which is the property of being normal. Okay. So let me define this. Definition. So let G be a group And well, this time H will be a subgroup. And maybe I'll just use a different letter actually. And let L be a subgroup of G. We say that L is a normal subgroup denoted, so this is the notation for normal subgroups. It's a triangle pointing towards the subgroup. If the following is true, well, in fact, there are several equivalent properties of being normal. Let's start with the one that is easy to remember. The set of right coset, every left coset is equal to its right coset. Namely, if GL is equal to LG for any G in G, right? So the left cosets are the same as the right cosets. That's easy to remember. Equivalently, the statement, let me just get it right. For any x in L and any G in G, the conjugate G inverse xg is in L as well. I.e., L is a union of conjugacy classes. Okay. Okay, that's also easy to remember maybe. A subgroup is normal if it's a union of conjugacy classes. Yeah, because this just says that if an element is in L, then any of its conjugates is also in L. In other words, L is a union of conjugacy classes. Okay, so this is the definition. Let me show you that these two are indeed equivalent. Yeah. Proof of the equivalence. The equivalence. Well, suppose that, let me call it 1 or 2. Let's prove that 1 implies 2. Well, given x in L and G in G, the element xg clearly belongs to LG, yeah, because x is in L. But this is supposed to be equal to LG by 1. Therefore, we can write xg must be equal to something from L times G. So to some element y, G, with y in L. But now multiplying this, yeah, sorry, GL, right, GY. But now we can multiply by G inverse on the left, yeah, and deduce that G inverse xg is equal to y, so it's a member of L as required. Right? That's what was required, right? That G inverse xg is in L. Okay? So 1 implies 2. Now to prove that 2 implies 1, right? So suppose that I have an element gx, which is in GL. So basically x is in L. And I want to show that it's an element of the other coset, LG. Okay. Well, we can write gx. We can write it as gx g inverse g. Okay, which in turn is g inverse x g inverse g. Okay, so if I call this element here y equal to g inverse x g inverse. Now this element is in L because of 1, because of 2, right? By 2. Okay, but then this thing is therefore yg is then in LG, right? So I started with an element of GL, and I proved that is in LG. Hence, GL is inside LG. Conversely, let's start with an element in LG. Let's start with an element xg, right? And then I'm going to write it like this. xg, I can write this g times g inverse xg, like that, right? And now this is in L. Again, by property 2, by 2. And therefore, this is inside GL. Okay? Therefore, I've proved the converse inclusion. Hence, I started with something in LG and I proved that this is in GL. And I proved the opposite inclusion, and therefore LG is equal to GL for GL as required. Okay. So this proves that the two properties 1 and 2 are equivalent, and we call a subgroup normal if it satisfies either of them, both of them. Okay, so you can think of either that a normal subgroup has the property that the left cosets coincide with the right cosets, or you should also, sometimes it's more useful to think of it as a union of conjugacy classes. Okay, I'm going to give more specific examples about normal subgroup in the next lecture, but now what I want to do is to show that the kernel of a homomorphism is actually a normal subgroup, not just any subgroup, but actually it satisfies this property of being normal. Okay. So let me just state it, and prove it in the last remaining minutes. let's add it immediately after the proposition. Let F from G to H be a group homomorphism. Then the kernel of F is in fact a normal subgroup. Of G. Okay? Okay, let's prove it. Again, at this stage, all the proofs should follow rather immediately, almost straightforward from the definitions. And indeed, this is the case. Let X be in the kernel of F. We need to show, and let G be in G. We need to show that G inverse XG is in the kernel of F, right? I'm checking property 2. Yeah. You see, even though 1 and 2 are equivalent, in practice, this is kind of easier to check because it talks about specific elements. I mean, 1 looks very neat, but in order to check it, you really have to check every coset. Every light coset is equal to every red coset. This is much simpler to check. Yeah. So this is what I'm checking. And of course, how do I check it? I just apply F to this element. F of G inverse XG is now, by the property of homomorphism, we know that this will be F of G inverse times F of X times F of G. But X is in the kernel of F, so F of G, F of X is the identity in H. So I can just cancel it out. So this becomes F of G inverse F of G, which is of course the identity in H, and therefore G inverse XG is in the kernel of F as required. Stop. So that completes the proof. Yeah. So the kernels of homomorphisms are kind of these normal subgroups, and I think I have a couple of minutes. So let me just emphasize that normal subgroups are far more special than subgroups. So let's give an example of a subgroup which is not normal. Example of normal, not normal subgroups. Okay? Let's do examples of a normal subgroup. E.g., suppose G is S4, permutations on 4 things, and I take the Klein 4 group, we'll call it L, is the Klein 4 group, namely the identity and the double transpositions, right? 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3. We know this is a subgroup. This is a subgroup. In fact, a normal subgroup. Right? Why is it normal? Well, because it contains the identity, which is one conjugacy class, and the other 3 elements are the conjugacy class of double transpositions. Yeah, we prove that conjugacy classes in symmetric groups are characterized by cycle type. So these are all the elements which are of cycle type 2, 2. Yeah. On the other hand, if I take L to be the identity and the cyclic group generated by the 3 cycle 1, 2, 3, this is not a normal subgroup. Right? Because these 2, 3 cycles are not all the other. These are not all the conjugacy class. Yeah? Because, for example, 1, 2, 4, since 1, 2, 4 is conjugate to 1, 2, 3 in L, but 1, 2, 4 is not in L. Right? Right? Okay. And a more elaborate example that I'm going to return later is if I took G to be the alternating group A5, its only normal has normal subgroups only the identity and itself. Okay. I'm going to prove this in the next lecture. And such a group is called a simple group, a group which has its only normal subgroups, the obvious ones. Yeah, so these are always normal. Okay. And simple groups play a big role in group theory because they're kind of the building blocks from which you can build other groups. And this will become clearer in the coming lectures when we discuss the first isomorphism theorem and then move on to group actions. Thank you very much.